Hello, everybody. I'm just moving all of the communication now from the Zoom conference call that we're in, into this YouTube live stream. So hopefully everyone can hear me. I just want to double check that we have a connection that's all the way through. So if you can hear me, please wave. I actually now set it up so I can see you right in front of me, which should be easier. Okay, good. So that's the ping time. This is sort of like waving across a stadium. I think 2 seconds might be about the same amount of time it takes for sound to get across a stadium. Okay, great. So let's go ahead and start. And the beautiful thing about this class is that the size of this class happens to be just right so that I can even see everybody on the screen at the same time. You know what? I'm going to close this particular thing, this participants piece, close. Good. So now I can actually just see lots of people's faces. And that makes it a lot easier for me to teach anything. Okay, so I want to continue with this regularity lemma. And so last time we started proving the Semeredi regularity lemma, and I just want to continue from where we left off. I must say, it actually turns out to be more convenient to do this with all of the existing previous screen recording. It's a little bit different from a classroom where I need to walk in and I need to like rewrite everything on the board. Actually, we can pick up exactly from where we left off, and that's also going to help because then I can already start talking through. Let's review where were we, right? So this will be a very quick review of where we were. So again, the goal of the regularity lemma is to prove that there is a way to partition into some t number of parts where the number is not too big, that's the exciting part of the regularity lemma, not too small so that it's useful. And also here I'm going to put one rubbish bin, v0. All we're going to say there is the v0, it can't be too big. Okay, so there's some condition on v0. And the key is that almost all of the pairs are epsilon regular. That's what we'll want. Now, the way that our strategy was for this is we defined an index. The index is this Q, a Q of a partition. And what this index is it's sort of like saying we're going to randomly choose two vertices. And these two vertices, which I choose uniformly at random from all the vertices, let's figure out what is the squared density between the two blobs that they happen to be in. That's what this is doing here. And we're going to do the squared density and find the expected value of that. The reason why that's interesting is because if I just found the expected value of the normal density, as Fei and many people observed last time, that would just tell me basically the edge density of the whole graph, which is not very interesting. Okay, well, close. It would be up modulo some things about, the edges inside clusters. Okay, so that's what we have here. And the strategy was, let's go and show that this index keeps increasing. And furthermore, whenever I'm not whenever I'm not in this final winning condition, then I can show that this index went up by some big amount, where big just means bounded from below. Then what did we do? The next thing we did is we said, okay, we were talking about the index of the whole partition, so now it's actually the sum of a lot of indexes of pairs, where I'm just saying this QUV is just one of these terms that we're summing over. That makes the notation a bit easier when I eventually start talking about the contribution to this index from between almost like a bipartite structure of clusters to another bipartite structure of some clusters to some other clusters. The first key lemma was to show that if I have, looking at just two different, again, this bipartite structure of these clusters, the index contributed by all of these things to all of those things, once you subpartition, is bigger than the index that's contributed by those two parts before. Okay, good. Wait, I just realized I should probably say something about homework. I understand that the homework was supposed to be due like last week. I said, let's make it due this week. I also know that some people wrote to me saying that because they even had to travel to other countries, it was difficult. This is not a very strict due date. I actually understand that the time here is very difficult. If for some reason you have difficulty sending in the homework today, just let me know. We'll be able to make everything work out. Okay. But back to here. So the index is rising between these two different, like this bipartite type structure. And then the lemma 2 was just use that in one step. Oh yeah, we proved this. But the lemma 2 was you use that in one step and you now show that the index always rises whenever I just subdivide. So if I have a partition and I start subdividing, I'll never have to worry about the index falling back. But there was one important part of the proof that I want to use. And that important part of the proof was something about the variance. It was that the index rises, the contribution of index in between these two rises by an amount which is exactly equal to a variance. And that's going to be the secret that shows that we'll be able to stop this process eventually. In fact, this whole proof I'm claiming is actually fairly intuitive, although the first time I learned the proof of the regularity lemma and I read some papers about it, it didn't look this clean. This is a proof that I think is in the Noga Alone and Joel Spencer's book, The Probabilistic Method, 3rd edition. And this is, to me, the cleanest version I've ever seen. And so, again, it's basically observing index rises by variance. So now, could I just go and try to show that if I'm not done, then there's a lot of variance? Where not done is back to here. Not done means not all but less than or equal to epsilon t squared pairs are epsilon regular. Let's find out. So let's now get some clean page. And now let's say, maybe we can call this lemma 3. If in the current partition there are more than epsilon t squared pairs which are not epsilon regular, then what we want to show is that there's a way to find a subpartition, a refined partition, sorry, not a subpartition, a refinement of the partition, where the index goes up by at least some amount depending on epsilon. Then there exists a refinement, partition prime, where the index of partition prime, P prime, is at least the index of what we had before, plus something. And we'll work out what this something is. Now, the key is I need to use this part. I need to use the fact that there are more than this many pairs which are not epsilon regular. So let's do a proof. I guess we should look at what happens when there's one particular pair that is not epsilon regular. So let's just focus on one particular pair. For without loss of generality, let's focus on V1 and V2. Suppose that this V1 and V2 is not epsilon regular. And of course, there will be at least epsilon t squared many of such things. So if that's true, let's see. I need to find some refinement. If I want to find some refinement of this partition, how might I try to do that? I guess I could try to find a refinement where I'm going to break apart V1 and V2 into some parts. And by the way, there's going to be more stuff that we're going to have to deal with too, but let's just focus on this first. Refinement means that I'm going to cut them into some pieces. How many pieces should I cut into? I don't know. How about 2 each? That sounds like the simplest thing to do. Does anyone have a suggestion of a natural way to use maybe a definition we've already been seeing throwing around here, a natural way to choose how to make that partition? And the only thing I'm saying is they're not epsilon regular. Feel free to, you can actually physically raise your hand if you want. Sorry, that only works if your camera is on. If your camera is not on, you're welcome to press whatever, the yellow hand raise or whatever. But I can see right in front, so if anyone wants to answer this question, I want to know what's a reasonable way to decide how to split the V1 and the V2. I want to split into 2 parts. And the only thing I get to play with is that somehow not epsilon regular. How could that be useful? How could I use that to define? Philip, I see your hand raised. You'll have to turn your mic on.
Can we take one set from each side which witnesses the lack of epsilon regularity?
He's saying let's take one from each side that witnesses the lack of epsilon regularity. Why not? I'm trying to show how this is extremely natural, okay? So we'll actually just choose those sets so that that happens to be the not epsilon regular, like the witness to not epsilon regularity. So I'm using this yellow circles, and I'm going to say you split so that somehow this split witnesses the not epsilon regularity. What I mean is, I guess I need to almost give some names. Do I need to do that? Yeah, I need to give them some names. So I'm actually just going to call this one B. I was about to call that A, and then I realized it would just be annoying if V1 was B and V2 was A. So that's the B, and this is the A. Okay, so I split it so that the density between A and B is wrong. So what we're saying is that the density between A and B is like too far, okay, I'm going to write it like with these absolute value signs, minus the density of V1, V2 is too much. It's bigger than epsilon. Okay, maybe I wrote bigger than, maybe it was bigger equal. Those are not going to be important for me here. Okay, so we're going to split like this. Now, why is this interesting? The reason this is interesting is if you just focus right here and say, we're just going to do one refinement from P to P prime, and the only refinement is we split each of those. What can we say about the index contribution? So let's maybe write down. We have an index of, oh, I need to give these some names. Let's just say it this way. Index of the refinement I also want to be clear. Yeah, I think I can do this. I can do this. This is the refinement on the full scale. So remember, there's like this whole P prime. I mean, there's all this P and all this P prime. There are all these V's. There's lots and lots of V's. There's T clusters, like V1 to VT, and there's even a V0. So this is the refinement of full partition. Okay, minus Q of the current partition. Notice I didn't call the first one P prime because we'll have to do a few more things to get to the P prime. But minus the Q of the P, what is this at least? Now I need to go and look at what control I might have. So first of all, as I do this split, I'm going to have all these other V's around. So there's another V3 and so on. What inequality or what fact could I use to try to get a lower bound on this? There is something that I could use that's going to directly be using this piece, that this density does not match. I guess I'll flip back a screen. Let's go and try to see what inequalities we might have. In fact, we have only one inequality here. We have this piece. This piece is talking about what happens between two particular clusters as I refine the partition within those two clusters. We also saw something over here, which was, between this one and that one, there might be some increase. There might be some increase in the index, but I'm going to even give that away. It's at least 0. So if I look at how everything comes together, over here, even the refinement itself is going to pick up by the size of each cluster multiplied together, divided by the n squared, which is somehow taking into account how much of the edges this can take how much of the edges this occupies, in the sense that if I had a complete multipartite graph, this first quantity is the fraction of edges consumed by this piece, times this variance of z. What's that? Let's go back here. So what I'll write is, I'll have to take into account the size of each of those clusters. What's the size of each of those clusters? I don't quite know yet. I'm going to call it m, but we're going to get a bound on m in a moment. It's at least m times m over n squared times the variance of this z. And what's m? So remember, there's also this other cluster V0. That's the rubbish. But we're saying that each of these has size m. Each of these clusters has size m. Okay? So why is this interesting? The first thing is that what is m over n squared sort of like? What's it close to? What would you expect? And we'll do some real inequalities in a moment. But this is trying to show where this whole proof is going. Do people see what this m over n squared, like, about what should that be? Assuming I did my job right, and assuming that this V0 is very small. Yes, Anthony? Yeah, it's got something to do with n and t. You see, because this m, right, so the m, because this V0 is annoying, right? And I heard that maybe they use it like an over 2. We will in fact use an over 2 for our hard inequality. But if you want to know, like, roughly what this is, the m is roughly n over t. So this is going to be of the order n over t times n over t over n squared. That's good because that's like a 1 over t squared. I'm just showing you why we're going in a good direction. So I'm going to say this thing. This is going to be about n over t over n squared. And that's about 1 over t squared. Okay? So that's good. That's good because, you see, there's another thing up here. the reason why the t squared is good, is 1 over t squared, it's because somehow using this one pair that was not epsilon regular, I got a contribution of like 1 over t squared, and there's going to be epsilon t squared, many of them. T squared is going to cancel t squared. That's how you know that you're on a good track. So now the var z. What was z? Variance of z. Let's go back and look at what was z. Z. Z was defined as, we've got these two clusters. Z will uniformly at random pick a vertex somewhere here, and then pick a vertex uniformly at random somewhere there. And then the Z is going to talk about the density that I have between them, okay? The density between the blobs that contain those vertices. How can you show that the variance of Z is actually big because of the fact that we split this way? I'm going to draw another picture so that I can just focus entirely on that. Here's another picture. I have my V1. I have my V2. I split them. This was the A, and this was the B. And recall that Z was equal to just the density between the cluster, well, the part with each vertex. I hope that makes sense. D is actually a function of two arguments, but I'm just trying to write this as condensed as I can. We're going to pick one vertex at random here, one vertex at random there, and I'll look at the density between those two parts with each vertex. How could I try to show that the variance of Z is big? On the one hand, the way we got the inequality last time was we said that the variance was equal to, this expected value of Z squared minus the square of expected value of Z. That's how we got an inequality earlier. But there's another definition of var Z which is very useful. What's the other definition of the variance? If I don't just go and say, take expected value of Z squared minus square of expected value of Z, how else could you define variance? Or rather, I should say, what is variance? And the other thing I told you is a consequence of that definition. Matthew. Matthew, you'll have to unmute.
It's sort of like, it's sort of like how far it is away from the norm.
It's like how far it is away from the mean, right? Yeah. So in particular, the variance is also the expected value of, it's the square of Z minus the expected value of Z. It's the expected value of the squared distance, okay? Now, the reason this is exciting is because the thing inside the expected value is a non-negative quantity. So what we have in here is this is the expected value of something that's always bigger than or equal to 0. So now I have a random variable that I'm taking expected value of. Sorry, it's the random variable is inside. I'm taking expected value of it. And by the way, that random variable is always bigger or equal to 0. The reason that's powerful is if I can tell you that there's a region of my probability space where this thing inside the expected value is like bigger than something, then boom, my variance is at least something, because I don't need to worry about the rest of the probability space, because on the rest of the probability space, at least my thing was non-negative. What am I getting at? Can someone close the loop? We have this epsilon regular business. How can I close this loop? We know that the A and B witness non-epsilon regularity, so how can I now conclude that the variance has to be at least something? Feel free to raise your hand. Liam, are you raising your hand or like scratching your head? I'm not sure. Okay. I guess that was a no. Anyone want to see a bound that I can make? Remember that A and B witness non-epsilon regularity. So I just need a region of probability space. Kirtana, I think I see you raising your hand.
It should have at least epsilon square because D of AB
Okay.
would deviating by at least epsilon.
I'm hearing this. What I hear is that there's an epsilon squared involved. And what we're seeing, I'm going to write more than there's this epsilon here, okay? But I'm just going to draw a picture. I'm going to say, look, if you happen to pick a vertex here and pick a vertex there, if you picked vertices in A and B, then your Z, which is, by the way, the density, it would be the density of AB, And this is too far away from the expected value of z. Oh, maybe I should have mentioned, we calculated last time, the expected value of z is just the density between v1 and v2. That was what we calculated last time. So the density, this expected value of z, by the way, this expected value of z was just equal to the density between the whole thing, v1 and v2. And that one was just like, look at the expression and multiply and simplify. That was not rocket science. So in particular, because this AB witnesses non-epsilon regularity, then I actually get that z minus the expected value of z in that region is going to be at least epsilon. Okay? Maybe I should have written bigger equal, maybe I should have written bigger, I don't know. Again, I'm not very careful with these pieces because that's not the most important part. Okay, so now that I know this, that means that on this particular part of the probability space, if I happen to pick in A and in B, then my payload, like the thing that I take expected value of, is at least epsilon squared. So I heard the epsilon squared come from Kirtana, but I claim you have to multiply by something else. So it's not just epsilon squared, I also have to take into account the chance. Ah, Matthew, I see your hand.
You need to take into account the chance that you pick something within A and B.
Right. You have to take into account the chance that you pick something in A and B.
A and B are epsilon regular. They both have to be at least some certain size.
Yep. So the way to think of this is that this comes from two parts. One of them comes from the let's call it density too far. One of them comes from density is off. That's one of the epsilon squareds. And the other epsilon squared comes from the fact that the A and B themselves are not too small. Like remember, epsilon regularity as a definition required that A is at least epsilon fraction of the V1, B is at least epsilon fraction of the V2. And so this is beautiful. Actually, the first time I ever saw this proof, I was like, I've never seen it explained this clearly before, why there's an increase in this index. Because what we're saying is that the variance itself is actually exactly what happens from the fact that this pair was not epsilon regular. Because it's not epsilon regular, by choosing the split for the subpartition in this way that follows the not epsilon regularness, I will pick up epsilon squared times epsilon squared. Just like that. So I'm going to write that down in the previous one. That gave me var z, and that's epsilon to the fourth. People still with me? So I'm trying to show you this is not actually a very scary proof at all. So effectively what we did is we now used the fact that I know that on this particular pair, I'm already going to grow by at least epsilon to the fourth over t squared. And by the way, I'm going to possibly grow a little bit more in my index anyway, because between v3 and the subdivided v2, I could get more, right? Whenever I subdivide, I could get more. But I don't even need that. I already have this bound. Okay, what should I do next? I hope that maybe some people see what would be a good thing to do next. Right here, I still have an approximation, so I'll have to deal with that later. But I'm like, why am I happy already? I have a 1 over t squared epsilon to the fourth. What would I want to do next? Liam, I see your hand.
Isn't that enough to just argue that with every subdivision that's picked appropriately, you're increasing by a constant amount, so the index is strictly rising?
Correct. So what Liam... Yeah, so what I'm hearing you say is that somehow just do this for every pair that's not epsilon regular. And remember, we already showed that we can subdivide and subdivide. So again, I'll return to this screen because we're going to have to worry about this approximation. We'll deal with that later. But schematically what's happening is that I have my V1, I have my V2, and there might be a V3. There are, of course, going to be all these V's all the way to Vt. There's also a V0. And what we are going to do here is we're going to say that we're going to start splitting apart each of these pieces. And as we start splitting apart each of these pieces, maybe the V1 and V2 split like this. But then the V1 and V3 might also be not epsilon regular. If not, I'll do this. But the key is, as I do these splits, I will actually do the sort of the product of those splits on the V1, if that makes sense. For each of these pairs, I will know that I have a split which is going to be compatible with the non-epsilon regularity of that pair. I want to emphasize, I'm not going to like do one split and then got a new partition of v's and do another split and got a new partition of v's. I'm saying I've got my all equal size, all of these different v's, and I looked through all pairs. For every pair, I sort of decided how I'm going to cut. And because of the fact that when I take sub-partitions, refined partitions, that the index keeps rising, I actually can then say, as I've done this all the way around, I will be able to have the index go up by at least epsilon t squared, which is the number of pairs. Now, index of this like very refined, it's still not p prime yet, minus the index of the original p. Actually, that looks ugly. Index of the original p is going to be at least, there will be epsilon t squared opportunities to do this, times whatever I had before. What I had before, I'm going to write in blue because it wasn't quite accurate, 1 over t squared, but the epsilon to the fourth was accurate, epsilon to the fourth. And so that would be great, because when I do this, it all multiplies, it cancels, and I would be able to show that the index rises. Is this clear? Are people happy with this so far? So I'd be able to show that this index keeps going up. There's one thing I want to also do here. It's that, actually, how should I define index with regard to the V0? We are soon going to start adding things into V0. Because at some point, as I'm doing all of this, I mean, this is not yet the P prime, so I'm saying this very refined. But if you look at what's going on here, if I try to do these cuts, I'm going to get lots of different size pieces. The V0 is going to be used to round off those pieces. So in fact, what I want to also say at this point, which will be helpful for going forward, is in fact V0, I'm not going to think of V0 as one part. I'm going to always think of V0 as a lot of singletons, meaning it's just one vertex by itself. In fact, V0 is always going to be lots of parts. V0 is always going to have as many parts as there are vertices. Each singleton, well, each vertex is its own part. And that's in this P and in this P prime that we will get. So as we're refining these partitions, the way it's going to work is that we'll have some big pieces, V1 to Vt, that we're calling the nice ones, all equal size. And we'll also have a lot of things that are in this V0, where all of them are like size 1. Okay, that's going to be very useful in what we'll do next. But so that's the layout of what we're trying to do. This, by the way, is still consistent with this inequality that I've written. Because in this inequality that I've written, these guys don't really matter anyway. If I look at this guy versus one of those things, yes, that index will even go up a bit more because that's being subdivided. Okay, so now the thing I need to address is the blue, 1 over t squared. What's going on there? So now I actually need an inequality. So over here I wrote 1 over t squared, and over here I wrote approximately equal to. The inequality I need is bigger equal. But now I think that was maybe something that maybe Anthony had said earlier, which was this m, it better be close to n over t, because anyway, I need to know that this rubbish is not too big anyway. The rubbish is supposed to be at most epsilon times n. And epsilon, by the way, is probably going to be a small number. We wouldn't apply the regularity lemma unless epsilon was very close to 0. So in fact, what you can say is that this approximate equal, I could actually replace it with adding another 2. I could actually say that we will enforce, how do you spell enforce? Enforce that m times m over n squared is always going to be bigger than 1 over 2t squared by checking at the end that the rubbish, V0, really was at most this epsilon times n. Okay, and the only time you would ever apply the regularity lemma is when epsilon is really, really small anyway. Are people okay with this? So what I'm going to say is we will do some work, and at the very end I'll show you, hey, by the way, all the rubbish that we ever accumulated, it doesn't add up to more than what would make me have to like put a 1 over 2 here. Okay? Okay, so at that point, we'll be just putting another 2 here. I'll put a red 2, put a 2 there. And if there's a 2 there, it doesn't matter to us. We go back over here, and we just get a 2 here. but now it's rigorous. And so when you put the whole thing together, we will get that it's epsilon to the power 5 over 2. And that so far has given us a partition where the index has gone up by at least this amount, but unfortunately we're not done yet, because we need that all of the parts in our official V's are all the same size. However, I'm already going to write that in the blank. The goal of what we're going to prove is at least epsilon to the 5 over 2. So there was a blank, and here I'm putting in the blank epsilon to the 5 over 2. Okay, so that's what we're trying to prove. Now, I need to show how to make them all the same size. If I want to make them all the same size, the secret actually is that we're going to be getting some horrible bounds on how big this M is anyway. In fact, if you think about what's happening, the M was like an upper bound on how many parts there are going to be. Do you see how many parts we might actually potentially get with this? So you see before, so I mean, I need to make all the parts the same size. But before I even made all the parts the same size, I used to have T parts. How many parts could I potentially have at this point after doing all of this splitting? Let's just make an observation. You can feel free to raise your hand at the same time as I start labeling this observation. The number of parts now, and I'm not counting the V0 parts. Number of parts, not counting the V0 is at most, I want a bound. So I had T, Anthony, yes. I had T parts before. How many might I have now?
In the worst case scenario, if you assume that all of the buses were epsilon regular, you could have T choose T.
Okay, you're saying in the worst case, like if none of the pairs were epsilon regular, you might have like T choose T. You mean T choose T? I think I misheard you. What exactly did you say? Say again? T choose T. But T choose T is 1, so that's not going to be a big deal. I think what I'm saying... T choose 2. Okay, yes. Yeah, so in some sense, I could have T choose 2 of these splits happening, right? And the way I'm going to think about it is how many times do I slice any particular part? I'm just going to do a dumb bound. And you're right, you might have T choose 2 such things. And if I want to know how many parts I might get, well, I had T parts before. I'm just going to write it this way. There were T. This is parts before. And you're right, there would be up to T choose 2 things that you do slicing of. But if I'm saying how many times I expand, it's that if you look at each of these pieces, I just need to know how many times I slice it, if you know what I mean. It's like I had T things and I slice it. How many times might I slice it? Your T choose 2 is slicing it T minus 1 times. So I'll say 2 to the power T minus 1. And what this is if each Vi is sliced T minus 1 times. Are people with me on this? So it's like somehow that would be the worst case. And by the way, it might even happen because if I am allowed to, if I'm supposed to keep going until I have only less than epsilon T squared many non-epsilon regular pairs, I will actually often have a linearly many, we'll be slicing this thing linearly many times, like constant times T times. So the number of parts I'm getting now is that I used to have T, now I have T times 2 to the power T. That's big. This thing grows fast. I'm saying that somehow my number of parts is going to grow. At least it's going to grow by a bounded amount. And the number of times it grows is going to be controlled by the fact that my index goes up by at least epsilon to the 5 over 2. So I can't go up forever. On the other hand, because it's going to grow so much, this is what gives us the freedom to say, let's just be a little bit lazy and or sloppy. And the way that I'm going to make all my parts the same size is I'm going to enforce a block size for every part. What I mean is, I will say, even though this V3 only got cut into 2 pieces, I am going to subdivide each of those pieces into equal sized chunks of a particular size. I'll cut them into those equal sized chunks, and there might be some residue. Let me explain. So let's look at this. Let's look at this this V3, for example, and I'll say in the V3, we're going to cut the V3 into completely equal size blocks of a particular block size. And then the last one might be off. Okay, so in this picture, I don't know how readable this is, but I'm going to call this the residue. Okay, so what we're going to do now is that each part, cut each part into blocks of size, oh, I don't know. Let's say originally we had n vertices. Let's say n over 4 to the power t. Okay, so we're going to allow ourselves to cut into these really tiny blocks, but the reason we don't care as much is because we're already seeing an exponential growth. The point is we already know our number of parts is going to grow to like 2 to the power t, so why not? Let's make it grow to 4 to the power t. It can't kill us that much. Okay, oh wait, actually not n. Let's say m. I think it might be m. We'll see soon. We'll see soon whether I mean n or m. So m, by the way, is the size that they were before, and we're now going to cut them into m over 4 to the t. My inspiration for saying m over 4 to the t is because somehow that's going to help me control how much is missing. And also what that means is if I cut into m over 4 to the t, the number of parts that I might have is just going to blow up by a factor of 4 to the t in some sense. Because originally I had these sizes of m, and now my v's are of size m over 4 to the t. That gives me a growth instead of t goes to 2 times instead of t goes to t times 2 to the t minus 1, it goes to t goes to 4 to the t. And both are exponential anyway. That's how I know it's not a big loss. Okay, cut into these size. And what I do is you just throw all the residue into V0. That's why this V0 is convenient. V0, by the way, once you throw it in there, they become singletons. So effectively, this residue that I've marked, the residue is actually going to turn into parts of size 1. This, by the way, is the final p prime. So once I've done this, where I said I took this refined partition where I split each of the parts, each of the v's, with respect to what was not epsilon regular, okay, now I've got all these pieces. Now each of these pieces, I go and further subdivide into these tiny blocks of m over 4 to the power t, and whatever is left over I throw in the v0. The important thing to notice here is that now this has achieved the property that all of the parts in the official v's are equal size. Okay? This also has achieved the property that the number of parts that I have cannot grow too much. In fact, the number of parts I could have can grow by at most going with multiplying by 4 to the power t. Is that clear? Because every part size, the part sizes themselves shrank by that factor of 4 to the power t, so the number of parts is going to grow by at most 4 to the power t. I might even lose some more because of the residue. Okay? So this has achieved a lot of things. The only thing I need to check is that my rubbish didn't blow up. Because unfortunately, as I'm cutting off all this stuff and I'm throwing them in the rubbish, it would be very bad if as I do this, the rubbish bin accumulates until it's a lot of my vertices. I'm going to make a few of those comments like over here on the right. So what has this achieved? Once I do this, now, all parts, all v's, okay, not all v's except v0. All v's except v0 are same size, m over 4 to the t. Okay, and so that implies that the number of parts is at most t times 4 to the power t. And again, I'm willing to give that up because I was already going to give up t times 2 to the power t. Okay, and now how do I know that the rubbish hasn't blown up? Well, I need to collect, and I need to see what's the total amount that I might have thrown into the rubbish. Total rubbish, total additional rubbish is at most how much? How can I bound that? I'm saying that somehow I have all of these little rubbish pieces, right? And so how do I show that the cumulative rubbish is not too big? And then now you're going to see why I chose 4 to the t. Remember before, I have t times 2 to the t minus 1 blobs that I'm subdividing into these tiny, tiny pieces. And those tiny pieces are all equal size, except there might be some round off error. Can anyone see a bound on the total amount that I throw in the rubbish that actually leverages the fact that this was a 2 and that is a 4? Faye.
Is it like the product of these numbers?
It's the product of these numbers. Yes, it is. So what you do is like, well, I have this many parts to play with, and every part can contribute at most a residue of size the block. Does that make sense? If your block size is whatever, the amount of residue you could have is up to block size minus 1. It's like the modular arithmetic. Like, modulo 5,000, I could have up to 4,999. And so I just take how many blocks there were, how many parts there were, times the block size. So it's at most t times 2 to the t minus 1 times the block size, m over 4 to the t. And that's exactly why we chose 4 and 2, because this is going to give you a converging geometric sequence. Okay? Actually, it's going to converge better than any geometric sequence ever, because our t itself is going to blow up like crazy. Okay? Like already, if I simplify this, it's going to be what? T times, it's something. So this is going to be at most, m times t. Oh, great. I needed to have the t here and the m there. The reason I needed to have both is because m times t, well, I can do a bound. That is less than or equal to n, because there's a v0 as well. So this total rubbish that I've added is at most n over, maybe I can write 2 to the t. I could even use 2 to the t plus 1, but this is good enough for me. So now I know that every step that I do this, I'm going to pick up an amount of rubbish that is n over 2 to the t. Okay? So now how do I put the whole proof together? So first of all, what have I gotten? I've gotten that the number of parts is going to grow by not that much. Oh, let me update my lemma 3, because lemma 3 should also say how many parts that I had. Lemma 3 is like, there is this partition, okay, but this partition is not the most interesting thing. The interesting thing is that there's a partition, index has grown, and furthermore, the number of parts has grown by not too much. Okay, let's add a few more things here. A few more things, and number of parts is at most t times 4 to the power t. And we have at most n over 2 to the t more rubbish, more v0. That's what we've just proved, right? We've proved this complete collection of stuff. Now that we have this very clean lemma 3, how do we close the proof? Well, to close the proof, what you say is, it already looks like the amount of additional v0 I'm going to have is going to converge, because I'm going to add like n over powers of 2. But I can force this to in fact be smaller than epsilon. Right? I need to know that the v0 is less than epsilon fraction. How can I force? I mean, now that we have lemma 3, we can close the entire proof. We're basically going to iterate lemma 3 on a certain starting point. What starting point would I use? By the way, I can start with anything I want. I'm just saying, if I've got any partition P, which has the equal size parts and like not too big v0, what should I do? Can anyone suggest for me how I can choose the right starting so that this v0 never gets bigger than epsilon times n? This is like this is just like an analysis observation. I just need to know that there is a legit starting point. Anthony, are you raising your hand? Yes. Your mic is muted though. Yeah.
If you make t large enough,
Yes, you just make the first t large enough.
some logarithm of epsilon.
Some logarithm of epsilon. Yeah, I'm lazy to figure out exactly which one we need. But I'm just going to say that, you see, it's going to be n over 2 to the t with the very first t that I start with. So all this means is arbitrarily start with a partition into equal size parts, where the number of parts you have for that t is big enough number of parts that this sum will never get bigger than epsilon times n. Are people following that? It's because if once you have this t, the subsequent t is actually really huge. This is going to converge very fast. Okay? So what I'll say there is, as you want to use this lemma, you just start with an initial t which is big enough. Let me write that all down in the new slide. So here's the finish. Start. Okay, it's funny that the finish says start, but anyway, start with an initial partition into some t0 parts of equal size Okay, you'll start with some rubbish. I mean, the rubbish will be whatever is the round off, okay? We'll have that. And, sorry, the remainder. And the remainder rubbish. With the T0 sufficiently large so that the V0 accumulates to, well, it's going to be at most, it's going to start with whatever it was. So whatever it was at the beginning, there's some remainder. And the remainder rubbish, if it's T0 parts of equal size, let's see. So how much starts? Yeah, so the remainder rubbish is going to be whatever it started off before. If all the parts are of equal size, how much could I have left over? I want to say like T0. Is that right? Or is that not right? I want to break stuff into, no. It's like how many, yeah. It's like T0 parts. It's like, so if I want to cut, like, if I have like 1,000 marbles and I want to break them into 3 parts, then the remainder that's going to be left over is going to be at most 3. So it's going to be at most T0. That's how much remainder there was at the beginning. It's in fact T0 minus 1. Plus, now we're going to get n over 2 to the T0 plus the next thing is n over 2 to the something way bigger than T0. But in fact, I could even say T0 plus 1. That's for sure. I mean, we'll get at least one more the next time. Do it a few times. I can do an infinite sum. I will not go infinitely many, but it will converge. And when you add all of this together, we're just going to force this to be less than epsilon n. This is just called choose T0 wisely. Are people okay with this? This is now showing how you can enforce that the rubbish is never going to exceed epsilon n. Once I have that, now I know that even as I'm doing this process over and over again, the approximation I made earlier, or the bound I made earlier, where I inserted a magenta colored 2, going back here, this magenta colored 2, this is now legit. Because now the way that I'm doing this, I'm guaranteed that I'm never going to have this be too big. Okay, at the same time as I'm doing this, the number of parts is going to grow by this t goes to t times 4 to the t, but I have a bounded number of times because I know that the index is between 0 and 1/2. We did that last time. So since the index is between 0 and 1/2, I do it at most 1 over epsilon to the 5th times. So this is now giving us our m. Each iteration grows Q, the index, Q by at least epsilon to the 5 over 2, but Q is between 0 and 1/2. So there are at most 1 over epsilon to the 5th iterations. Now that's powerful because each iteration, each time, the number of parts goes from t to, well, less than or equal to t times 4 to the power t. So then now I have an m. The m is called iterate this function. T goes to t times 4 to the t. Iterate this function at most 1 over epsilon to the 5th times. Here, I'm just going to be lazy. I'm going to say, by the way, t times 4 to the t, that happens to be less than 5 to the t. That's generally true for most values of t. Okay, so I'm just going to put that. I think that's true. Is that true? That should be true. That should be very true. Okay, so now I have a nice iteration. It's called a tower function. Okay, so when I put all of this together, what this means is, so the m in Semeretti's regularity lemma has a bound. And that m is less than or equal to, I have my initial t0, whatever this t0 was. That's not the scary part. That initial t0 is, as Anthony said, it's like around logarithm of 1 over epsilon. I think that's what you said. Something like that. Around logarithm of 1 over epsilon. Do we agree? Yeah, around logarithm of 1 over epsilon. Something like that. So this part is not that big. About logarithm of 1 over epsilon. And then multiplied by, well, it's going to go, oh, wait. Actually, it's not even multiplied by. It's that goes to 4 to the power that. And then it becomes 4 to the that, 4 to the that. Sorry, let me erase this. I'm going to write all the 4s first. That's the big part. There's going to be all these 4s. fives. I wrote fives. So it's all these 5 to the 5 to the 5 to the 5. Lots of 5s. At the very top, I have a t0. The t0 itself is about logarithm of 1 over epsilon. But that's not the scary part. The scary part is how many of them there are. The number of 5s is about, well, it's bounded by, it's at most 1 over epsilon to the 5th. Okay, and it's finite. That's all we claim. The point of the regularity lemma was that it's finite. We got a tower bound. We don't actually care about the top one. But we got this nice tower bound with at most 1 over epsilon to the 5 many things in the tower. And that proves Semiretti's, that proves Semiretti's regularity lemma. Right? And that proves Semiretti's regularity lemma. So in the end, we're able to get a finite bound. Yes, it's tower. Unfortunately, there is a construction that shows that you cannot prove something better than a tower. There is actually a graph which resists regularity partitions of size less than tower. Because at first you'd look at this proof and say, well, I mean, actually, what was in this proof? In fact, not much. It's not like super, super deep. It's just a very clever use of variance. And so perhaps, maybe if you try harder, you could get a proof that has a better bound. And the answer is no, you can't, not significantly. So I'm going to recap this proof, even though we're over time, because I want to emphasize that this proof, once you have all of the pieces, is actually not crazy. So we're going to do the beginning recap super fast because we did that at the opening of the class. All you need to do is define the index. The index is expected value of squared density. Squared density is how you get value because normal density is nothing. It's just going to give you edge density in the whole graph. Show index rises. To show index rises, first do it with the bipartite version because that's where we get all of our mileage. On the bipartite version, the key observation is that you can compare expected z and expected z squared. Expected z was nice because, again, that's just edge density. Expected z squared is exactly what we were tracking, and that gap between this z squared one and the square of that is exactly the variance. Once you have the variance observation, that is the key piece that you need to show that you can actually get growth. This one is a relatively simple proof. This part is the easy part, that the index keeps rising. And then, once you want to show the index rises by at least some amount, in this class I went very slowly just because I wanted everyone to be able to appreciate how beautifully nice this is. You just simply show that your variance is big. And how you show the variance is big is by specially choosing your cuts so that your cuts happen to be exactly what witnesses that your z, your edge density, was off. And so for free, you actually get the epsilon squared times epsilon squared, epsilon to the 4th. You then put that together, and you do this all these many times at the same time. You will, because there are at least epsilon t squared many not epsilon regular pairs, the t squareds cancel, and you get epsilon to the 5th over 2. Bang! Now we get at least some amount of gain every time. Number of parts, they grow by, there's an exponential, but then you just simply use like a bigger power, like 4, to go and make sure that when I put everything together, I can have equal sized parts. And that rubbish just doesn't add up to very much because it adds to a convergent geometric series. It's bounded by convergent geometric series. And you put everything together, you get a tower type bound. That's it. That's the entire Semiretti's regularity lemma. So now we have proved this. Now all of these applications that we've used elsewhere in the class, now we know why it's true. And I encourage you, if you found this proof to be somewhat natural, in fact, if you just go and sit down and try to redo these steps that I did, you will come up with the proof. All you need to know is that there's some random variable z, and you just take a variance. It's a variance, and the whole thing falls out. And this is how I came to understand the proof. Before it was a mess to me, and then I saw this in the Alone Spencer book, 3rd edition, and I was like, wow, that's just beautiful. Okay, so that actually finishes up this class. Do people have any questions? Actually, let me do this. Since that finishes up the CMU class, I'm going to close down the Zoom. I'm going to close down the YouTube connection, and we'll chat with the CMU class. So see you guys next time.